Please mute all of him. You can see the screen now. One of you.
Yes, sir.
Okay. Okay. So in the last class, we started talking about this open system. Okay, because all our discussion so far was with closed system, so the composition remains constant. Now there are many cases in our many processes where actually system is not closed because you have a exchange of particles, motion exchange of material, whether it's a chemical process or any flow process or anything you are looking at it. Most of the cases you will see there is a exchange of matter happen. So therefore systems are actually open quite often. So in open system, you have exchange of matter. So therefore, you need to modify your or append your existing thermodynamic relations for a closed system to take care of the openness of the system. Okay. So now, in addition to pressure and temperature, now composition is also a variable because they also change. So therefore, you can write down the G like this. We already talked about it. So complete change in differentiate. If you differentiate, you get this type of an expression. Okay. And first two expressions are basically constant numbers, so they represent the closed system. So they are VdP minus SdT. We know that the fundamental equation for Gibbs energy. And then the third term comes here. This we introduce the chemical potential term here. So chemical potential is basically the rate of change of Gibbs energy with the composition. Okay. Now, if you carry out the measurement at constant pressure and temperature, then dG becomes simply this much. So this is basically, you remember when we talked about, we introduced Gibbs energy, we talked that change in Gibbs energy is a measure of the external work available or the non-expansion work available. So in this case, so it's basically this term, third term, that gives you the non-expansion work. Okay. So this is the definition of chemical potential. And this is the very important term in open systems. So we introduce this here, and this will be, we will talk about it. Okay. Why chemical potential is important? We will take one or two examples for open systems. Okay. Then we showed you this that chemical potential is such a function which actually can be measured by measuring the change of any of the thermodynamic variables, any of the extensive properties. Okay, but only thing is that you have to apply the appropriate conditions, and you can show that very easily. So this is the most common expression of chemical potential that we know, but it can be written in terms of other extensive properties also. So that's why it represents what it gives you. It basically gives you how the extensive property changes with composition, any extensive property. Suppose you can measure, you change the composition, and if you can measure how internal energy changes, then also you can find out chemical potential. Or if you can measure how enthalpy changes with composition, that can be also then associated with chemical potential, and so on. Okay, so it can be written in therefore different ways. Okay, so that is what we know about chemical potential. So we introduce chemical potential. Now we need to get some important thermodynamic equations, which are working equations, which are applicable for open systems. Now these are known as the Gibbs-Duhem relations. Now what are these relations for open system? Let us see. Now this is the expression of chemical Gibbs energy change. We discussed about it. So pressure, temperature, and the composition. Compositions are now variable because we are talking about open system once again. Okay, and this we know this VdP minus SdT plus this term we already introduced chemical potential. So chemical potential mu I into dNi. Okay, dNi is the small change in composition of the ith component. Okay, so this is the and multiplied by the mu that gives you the contribution to Gibbs energy change from that component I, and then you sum it over all the constituents. Now, if you straight away apply constant temperature and pressure, then these two terms disappear. So therefore, at constant temperature pressure, you can simply write Gibbs energy change is like this. Okay, Gibbs energy change is like this. So mu I dNi. Okay, this is actually one of the equations for open systems. Now, let us suppose that all the constituents that are present in my system, we change their composition by the same proportion. Say every one composition was changed by 10% with respect to its current composition, or 20%, like that. Okay, some kind of a fraction of that change. So each component changes is simply whatever it was into that fraction of change. Okay. Now, if we do that, then your Gibbs energy is an extensive property. It will depend on the amount of the material present, okay, or the number of moles. So therefore, Gibbs energy also will change, and it will change by the same proportion. Okay. So everyone's composition, if I change by say 10%, then Gibbs energy will also change by 10%. Okay, because this is an extensive property, it directly depends on the amount of the components present. Okay, so DG also change in Gibbs energy also, because of this increase in concentration of the constituents, it will be like this. Okay, so therefore this is the equation 1 gives you the change in Gibbs energy. So now DG, if I write G into delta N, and this one dN is actually Ni delta N, so we write it down like this. Okay, simply substituting this. So delta N gets cancelled, so you get this expression. So this is the Gibbs energy of the system. So Gibbs energy of the system is simply sum over chemical potential and the number of moles. So this is the, and sum over all the constituents. This gives you the total Gibbs energy. Okay, this is also an important equation now. Now, since this is the total change in Gibbs energy, the total Gibbs energy of the system, what is the corresponding change? If I carry out the change at constant temperature pressure, so I can differentiate this. There are two variables, mu and n, both can vary. So therefore, dGpt can be at constant pressure temperature. I can write it down like this: mu I dni and then ni d mu I. Okay. So this is the change in Gibbs energy at constant pressure temperature starting from this expression. But we already know equation 1 tells that this is the change in Gibbs energy at constant temperature pressure is given by mu dni, sum over all the constituents. Okay. So here you have an additional term here. So therefore this must be 0. So if I compare between equation 1 and equation 2, then I get this expression: n d mu, ni d mu I, sum over all the components, that is equal to 0. Okay. Now, so these three equations, what you have written, these are all collectively, they are known as Gibbs-Duhem relations. Okay, and they are applicable for open systems, because you see that now chemical potential and the compositions are involved in this equation, and how Gibbs energy changes at constant temperature pressure. This gives you total Gibbs energy. This is the Gibbs energy change. And we have another third relations, which is kind of an identity relations, Ni d mu I, sum over all the components equal to 0. Okay. Now this third equation has a very important significance. What is the significance? Suppose you take two components or a binary mixture. Okay. So according to this expression, therefore n1 d mu1 plus n2 d mu2 equal to 0. Okay. So therefore I can write down this d mu2, or one of the component change in its chemical potential can be written like that: minus n1 by n2 into d mu1. Okay. Now see this. What does it mean? Suppose I change the mu1, that means the first components, component number 1, you change its chemical potential. Then your what it says, d mu1 is positive, but d mu2 is negative. Okay, so that shows that that means even if I have not done anything with the component 2, okay, we have not changed its composition in component 2. If we change the composition of component number 1, okay, that also affects the change in chemical potential of the second component. Okay, so a change in mu1, first component, then mu2 must decrease. Okay, if mu1 increases, then mu2 must decrease because the mu2 becomes negative. Okay, so it shows that the one of the components, if you change the chemical potential, then every one other component gets affected. Okay, so chemical potential of one component in a collection of many in a mixture, it cannot change independently. Okay, so if you have a mixture of say 10 different components, you have put in a mixture in a system or in a container. Now suppose one of the components you increase or decrease its concentration in the mixture without affecting the others, but that will alter the chemical potential of all of them. Okay, so because of this expression, see, this involves all the components Ni d mu I. So the change in chemical potential, and if you multiply the number of the component, then that becomes actually 0. That automatically means that if you change one of the components, then it will affect all the components' chemical potential value. Okay, so this is one important significance of the Gibbs-Duhem relations, that chemical potential of one component cannot change independently of that of other components. Okay, so any one component, two components, if you change the chemical potential in the system, then everyone's chemical potential will be modified. Okay, so this is an important significance, and these three relations are very important for open systems. If you want to understand the thermodynamic properties of the open system, then these Gibbs-Duhem relations are the fundamental equations. They are the starting points. Okay. Now, after this, we'll see why chemical potential we have brought in now. What is the importance of chemical potential? Okay, or their properties. Now, chemical potentials. Suppose this is we know. Okay, we have already discussed earlier that we know that how Gibbs energy changes with pressure. We knew that G equal to Z0 plus nRT log P by P0. Okay. Now, if you take, this is for ideal gas, of course, this is the expression we derived. Okay. Now, if you take per mole, just a pure, this is for pure gas. So if you divide by n number of moles, then you get per mole, and per mole we know Gibbs energy by per mole is nothing but chemical potential. So we can write it down mu equal to mu0 plus RT for 1 mole log P by P0. Okay. So this is the form of mu in terms of the pressure of the system. Okay. How it varies with pressure, that you can find, you get to know from these expressions. Now you consider one particular any process that is happening in your system. Suppose transfer of matter. It's one of the simple process that we are looking at. One example of a process is that transfer of matter. How it transfers? Suppose we take a system with there are two phases. Okay, there are two phases. Each phase may contain several components present in the phase. Let us assume that in this two-phase system, one of the components, suppose ith component, a small fraction of the ith component transfers from phase A to phase B. Okay, phase A, where its chemical potential was mu IA, and this phase B, its chemical potential was mu IA B. Okay, so we are assuming that the ith component, a small fraction of that dNi mole, it passes or transfers from left hand side to right hand side, A to B. Okay. Now we'll apply Gibbs-Duhem relations. What will be the change in Gibbs energy? Since there is a transfer of matter, obviously the Gibbs energy will change. It's an extensive property. It will change in both cases. Here it will decrease because it has lost the matter and the matter went to the B. So therefore its Gibbs energy will increase. Okay. So what is the Gibbs energy change for the phase A? That is simply chemical potential of that phase minus dNi, because this has been transferred to the other side. And what will be the change in Gibbs energy for the second phase B? This will be simply addition of that component. Okay, so ith component has come to the phase B from A, so therefore this is its change in Gibbs energy. Okay. Now what is the overall change in Gibbs energy? It will be simply sum of these two. Okay, so this phase A lost its Gibbs energy decreased, and this side's phase B Gibbs energy increased. So what is the net change? Is simply if you sum the two changes, then it will become like this. Okay, so mu I B minus mu I A, that means chemical potential of the ith component in phase B minus chemical potential of ith component in phase A. Okay, multiplied by the change in the number of moles or the fraction of moles that has been transferred. Now, looking at this very simple expression, you can see that there are three possibilities here. Okay, mu I and mu B, dNi is the fixed quantity positive, but mu I and mu these two chemical potentials, one of the two can be greater than the other and vice versa. Okay, or they can be same. So one possibility is that left hand side chemical potential of that particular component is greater than the right hand side. So mu IA is greater than mu IB. So if this is greater than this mu IA, then what happens? DG becomes negative. So change in Gibbs energy of the system will be less than 0. And we know that if Gibbs energy is negative, Gibbs energy decreases, then that is the spontaneous process. For any spontaneous process, DG is less than 0. Gibbs energy change is negative. Okay, so therefore, in such a case, there will be the transfer of matter. What we started, that a matter transfers from A to B, that will be a spontaneous transfer. Okay, so that means,
excuse me, sir,
for matter to transfer, chemical potential from the starting phase must be greater than the chemical potential of the destination phase. Okay, so if this is the case.
Excuse me, sir.
Case 2, yes.
Sir, here DG condition of less than 0, sir, but it was only valid for constant pressure and temperature, sir. But here, if we have some other kind of system, then how can we use the same equation?
No, these are under constant temperature pressure only.
Okay, okay.
We are keeping this at constant temperature pressure. See, it is written here. Okay.
Yes, sir.
So whenever you talk about Gibbs energy change, are generally at constant temperature pressure. These are not written here, but this entire process is done like that.
Okay, sir.
Okay. So this is just the change in Gibbs energy under constant temperature pressure. What is happening? At constant temperature pressure, you have two phases, then you are seeing some transfer of matter. Okay. So what happens to the Gibbs energy change of the two sides that we are doing? Now under this condition, this DG change in Gibbs energy is negative now. So in this case, it is spontaneous. If the reverse is the case, suppose chemical potential of the destination phase is greater than the this side, the starting phase, phase A, then DG becomes positive. Mu IB is now greater. So that means DG becomes positive, greater than 0. So we know if DG is greater than 0, that is a non-spontaneous process. That cannot be a spontaneous under that condition. So there will be no transfer. Okay. So there will be no transfer of matter from one phase to another if the chemical potential of the starting phase is lower than the chemical potential of the destination phase. Okay. And third condition is also possible, that the chemical potential of both the components are same in the two phases. So chemical potential of component I in phase A is same as the chemical potential of component I in phase B. This is also possible. Now, if this is possible, then DG will become 0. So Gibbs energy change is 0. That means the state is at equilibrium. So at equilibrium, chemical potential will become same of the component in the two phases. Okay. So this is the three important case. So what it suggests? It suggests that you have a transfer of matter from one phase to another will be spontaneous if it occurs from region of high chemical potential to the region of low chemical potential. Okay. So in any process, the process to happen, okay, it must occur from the region of high chemical potential to the region of low chemical potential. You should see the transfer of matter. And at equilibrium, the chemical potential of the component should be same in all the phases. So then you will not see any further transfer of matter. Okay. So therefore, transfer of matter always happens from high chemical potential to low chemical potential side. Okay. You see, this is similar to what we know about electric potential and all that. That is why it is called chemical potential. The term potential comes because we also know that current flows from high potential to low potential, high electric potential to low electric potential. And when the electric potential difference becomes the same, then current flow stops. Okay, because system some sort of equilibrium is there. Exactly same thing happening here. Instead of current flow, we are talking about the flow of matter or transfer of matter from one region to another region in the system, or from one system to another system, one phase to another phase. So condition for that transfer to happen is that this matter must flow from the region at high chemical potential to another region at low chemical potential. Then only that transfer is spontaneous. Okay. And the other way it is not possible. Like current cannot flow from low electric potential to high electric potential point. Similarly, matter cannot be transferred from low chemical potential region to the high chemical potential region. Okay, that becomes non-spontaneous. And if the chemical potential of two phases or the two sides are same, then there is no transfer at all. So because the two phases are basically at equilibrium. So chemical potential, therefore, is a kind of a measure of equilibrium, and it is also a measure of the spontaneity, in which what will be the direction of the process. That is why it is very important. So you have to know the chemical potential of the 2 points between which you want to see whether transfer of matter is possible or not. Okay. Now, depending on the sign of the chemical potential, if the difference is positive or negative, depending on that, the Gibbs energy change will become positive or negative. If you find out that Gibbs energy change is negative, then automatically that particular process is spontaneous. Okay. So this is that is why chemical potential is a very, very important quantity, because it is connected with the spontaneity. Okay, spontaneity of a reaction that occurring in an open system, okay, where there is a flow of matter. So any kind of flow of matter, suppose you are starting a diffusion across some kind of a barrier or across a membrane, or transfer of matter. Okay. So in order to make that spontaneous, you have to make sure in what should be the gradient in chemical potential. Okay, that automatically means the gradient in concentration. Okay, so that is why this is very important, and you also have a condition of equilibrium. That at equilibrium chemical potential must be the same. Okay. Now, see another, we will see chemical potential, how it is important is when you talk about an ideal gas mixture. We talked about it earlier also when we discussed the entropy change for a mixing of gases. Now we are trying to see that what happens to the Gibbs energy change when you mix the gases. Okay. Now we are considering ideal gases for simplicity. Okay. Once again, this is our equations, G equal to G0 plus nRT log PP0, and if you do it a per mole, then G can be written as chemical potential. This is in the pure phase, mu equal to mu0, one component RT log P by P0. Okay. Now you take a mixture. Suppose you have a n number of different components. These are ideal gases. You have mixed them. Okay, we know that mixing happens. So if we mix several components, then what will be the chemical potential of the component in the mixture? Okay, can be written is like that. In that case, the pressure will become the partial pressure of that gas, because now there are several gas molecules present, or gas types of gas are present. So you want to know what is the chemical potential of one of the particular gas component, then you have to take its partial pressure. Okay, so we write it down this mu I equal to mu0 plus RT log Pi by P0. So what is Pi? We know it is actually Xi into P, mole fraction is Xi, and P is the pressure of the gas mixture. Okay. P is the pressure of the mixing. After mixing of the gas, you have several gas components, you mix them. P is the pressure of that mixture. Okay. What is the individual component pressure? Is the partial pressure of individual components, can be written like that. Okay. Now, if Py is this, so from this expression we can write down Pi in terms of P. So I get Py0, Py0 plus RT log Xi P by P0. Okay. And then I can rearrange and write it down in this manner. Py0 plus RT log P by P0 I have separated, and then RT log of Xi. Xi is the mole fraction. Okay. Now, what is this term? First two terms, μi0 plus RT log P by P0. This is looks like a pure gas. One component gas has chemical potential. Okay. So suppose I write it down μi star, μi0 plus RT log P by P0. What is this mean? This is the chemical potential of the component I in its pure state when the pressure in the pure state is same as that of the gas mixture. You see now P, it is capital P. This capital P is the pressure of the mixture gas mixture. Okay. So that means if I take one of the components in a pure state and maintain the same pressure as that of the gas mixture, okay, then this will be the chemical potential of that pure gas. Okay. So this is basically the μi star. If I write down, then whole thing we can write down as μi star as RT log Xi. Okay. So this is the chemical potential of the gas μi star in the pure state, and μi is the chemical potential of the ith gas in the mixture. Okay. Now if you see what is chemical potential, chemical potential is always less than 1. It's a fraction less than 1. With less than 1, then this term is negative. Okay. So therefore, in the mixed state, in the mixture, the chemical potential of the ith component is less than its pure state. Okay. So chemical potential is less in the mixture, okay, compared to the pure state. So chemical potential of the gas I in the mixture is less than the chemical potential of pure gas at a given temperature pressure. Same gas, if you take under pure condition, that's chemical potential. And if you measure the chemical potential of the same gas in the mixture at the same temperature and pressure, then you will see that in the mixture, the chemical potential will be less than the chemical potential in the pure form. Okay, this is coming from this expression. Okay, once again, let us you see whether you understood this part. We are trying to show how chemical potential is important. So we have taken another example. We are mixing of ideal gases. Now mixing of ideal gases, you know, this is chemical potential, this is Gibbs energy. Okay. Now in the mixture, you always deal with partial pressure. So μi can be written as like that. μi0 plus RT log Pi is the partial pressure of ith component by P0. Now Pi can be written as mole fraction into total pressure. So therefore we write it down like that. And from there, this is basically essentially represent the chemical potential of the ith component in its pure form with the same pressure as that of the mixture, that is P. Okay. So the whole thing is that of for the pure state of that component. So in the mixture, the chemical potential is simply pure state chemical potential, which is appended by this term. Okay. So this is basically the mixing effect, RT log Xi. Okay. This is the pure state chemical potential of ith component at the same temperature pressure as that of the mixture, and which is modified by this term. So this is second term. This is just the effect due to the mixing. Okay, this is the effect due to the mixing, which is basically the composition. How much, what is the mole fraction of that component in the mixture? Okay. So due to addition of this term, now you see that mu in the mixture becomes less than chemical potential in the pure form, because X is less than 1. So this is negative. So μi, this you are subtracting from μi star. So in the chemical potential of the gas in the mixture, therefore, is less than the chemical potential of the gas in pure form at the same temperature pressure condition. Okay. So this is the first part. Now let us see what happens to the Gibbs energy change. due to mixing. Okay. Now, what will be the Gibbs energy for the mixture? We know Gibbs energy is given by this Gibbs-Duhem relation. We did G equal to mu n, sum over all the components. This is the total Gibbs energy change. So for the mixture, what is the Gibbs energy? Gibbs energy can be written like that, Ni mu I. Now mu I we have derived, it can be written like that. So we are using this expression so that the composition comes into the equation now. So we have Ni mu star plus RT n log Xi. Okay, this is the expression. Now what is Ni mu star? Mu star is the pure state chemical potential. Chemical potential means Gibbs energy per mole and numbered by the number of moles. So therefore this is the free state Gibbs energy of all the gases, and then you are summing over all the gases. So therefore G star is the sum of the Gibbs energy of each component when they are present in the pure form. Okay, once again, so G star is the free Gibbs energy in the pure form of all the gases when they are present in their pure form at the same condition. Okay, and this is basically the effect of mixing. So therefore, once you add this term, this gives you the Gibbs energy in the mixture. This is the pure form, and this is the effect of mixing. The effect of mixing comes from the second term, RT, this term. Okay. Now, if I want to know what is the Gibbs energy due to mixing, we have to subtract this G star from G. Okay. Then I will get what happens. What is the Gibbs energy happened because only mixing. Clear? Now this is something like this. Suppose you want to mix 10 different gases. So you keep the 10 different gases. First, how you do? You keep them in some containers separately in the pure form. You bring them from somewhere. You keep them ready. Okay. And then what you do? You basically keep mixing all of them one after another at the same condition, same pressure, same temperature where you are. So that is what exactly you are doing. So this is the pure form. It's a collection of all the gases parameters from here, and this what happens due to mixing. Okay, now because of mixing something happens, so that is why your G star, this is the pure form Gibbs energy, gets modified. So you are adding this additional term. Okay, so in the pure form, suppose you have 10 containers, if you measure their Gibbs energy, that is actually sum it up, that is G star. Now, after you mixed all 10 in one container, you have a G value that you measure in the mixer state. So therefore, what is the change due to mixing? Will be simply G minus G star. So this term is the change in Gibbs energy due to that mixing process. So delta G mixing is simply the subtraction. So this is the term. Okay. Now you can rearrange it. You can multiply and divide by the total number of moles. So therefore it becomes N outside, and here it is Ni by N, which is nothing but mole fraction. So just to write it down in a proper way, so we can write it down exactly same, identical expressions. nRT sum over Xi log Xi. So the mole fraction log the mole fraction of the component, sum it over all the components that you mixed at the particular temperature. Okay. Now this is your delta G mixing. This is Gibbs energy due to mixing. This was G was Gibbs energy in the mixed state, and G star was the Gibbs energy in the pure state. So we are subtracting that. We are getting what is the Gibbs energy change due to mixing. Okay, so therefore this is delta G mixing is simply this difference between them, which is this expression. Now, if we know delta G, this one, we can find out delta S mixing from where? Gibbs-Helmholtz relation, we discussed that last week. Okay, delta S can be written as minus del delta G by del T. Okay, so from where if you do that, from here you get with respect to temperature. So simply it becomes minus NR, temperature is here, and this term remains the same. So you get a minus NR this. This is the exactly same expression we derived when we talked about entropy of mixing. So you can see that exactly same expression we are getting from here. Okay. From thermodynamics, from Gibbs energy calculation also you can get change in entropy by simply differentiating it. with respect to temperature. Okay. Now you see delta H mixing, what happens? What is delta H? Delta G is actually delta H minus T delta S. So from where you can know delta H actually delta G plus T delta S mixing. So we know delta G mixing, we know delta S mixing. If you write down, you will see delta H is 0. Okay. So what you are seeing now, that due to mixing, there is some change in the Gibbs energy. There is some change in the entropy. Okay. But there is no change in enthalpy when you're mixing. Okay. So this is crucial. There is no change in enthalpy due to mixing. Why? Because these are ideal gas. As I was talking, someone asked questions in the before the class, that because they are ideal gas, this is a mixture of ideal gases. So there is no interaction between the particle. Okay, because they are ideal. So and the temperature is fixed. So therefore, there is no change. Interaction changes. So therefore, delta H does not change. So enthalpy change does not change, happen. There is no change in enthalpy. But still, you see, now from here, I think I've written it in the next page. See, xi is less than 1, we know mole fraction. So therefore, log xi will be negative. Okay, xi is less than 1. So therefore, ln xi is negative. So therefore, delta G mixing is negative. So delta G is less than 0 for the mixing of ideal gas. So therefore, a mixing of gas is always spontaneous. Okay. And delta S also you can see that will be positive because this term is negative, so it becomes positive. So when you mix gases, ideal gases, then what happens? Its delta G is negative. That means it's a spontaneous process. Okay. But you see the two things, delta H and delta S. These two makes delta G. Okay, delta G equal to delta H minus T delta S. So delta H and delta S, that means enthalpy change and entropy change. These two together is makes the change in Gibbs energy. Now here we are seeing there is delta S change happening. Even the gases are ideal, but delta H is 0. So that means the contribution of delta G mixing is only coming from delta S. Okay, or in other ways, all the driving force that comes when you mix ideal gases, the driving force comes from the entropy change. In other words, the mixing of ideal gases is an entropy driven process. It is not an enthalpy driven process because there is no change in enthalpy if the gases are ideal. Okay, so mixing of gases definitely spontaneous for ideal gases. Okay, and that spontaneity means delta G is negative. We found that, and automatically delta S is positive. So because delta S is positive, so delta H is 0, but delta G equal to delta H minus T delta S. So delta S is negative, so therefore delta S is positive, so therefore delta G is negative. Clear? If this is not clear, you ask this part. Okay. So this part is actually very important conceptually. There is no change in enthalpy when that means no interaction, no energy change, but still mixing of gas is favorable because delta G of mixing is negative. So that means it has to come from entropy change only. There are two parts in delta G. One is delta H, one other delta S. These two contribute in delta G. Okay, delta H and delta S contribute into making delta G positive or negative. Now in this case, delta H is 0 for ideal gas. So therefore, only component or only quantity that can control delta G is entropy change. Okay, so therefore mixing of ideal gas is an entropy driven process always, and because entropy increases on mixing, so therefore delta G becomes, when delta is equal to positive, so delta G is negative. Okay, because it is minus T delta S. Okay, so delta S is positive, so delta G remains, therefore becomes negative. So that leads to mixing of gases is a spontaneous process, we found. Now remember that spontaneity comes from the increase in entropy. Okay, so completely driven by the entropy of the constituents. Now, if you know this expression, now you know delta G goes down, becomes negative. So if you take two gas mixture, where will be the maximum, most favorable or maximum mixing, maximum decrease in delta G? You can simply take a derivative and put it to 0. We discussed that during the entropy change. Exactly same way. If you differentiate this, okay, with respect to X, one of the components, okay, and then plot it. So you will see, put it to 0, you will see that maximum change in Gibbs energy negative, that change happens will come when this mixture is x1 equal to 0.5. That means 50-50 mixture. If you have a two component system, if you do a 50-50 mixture, then you'll have a maximum decrease in the Gibbs energy. And maximum decrease in Gibbs energy will be associated with maximum increase in entropy. Clear? This is maximum increase happening here at x1 equal to 0.5, and your expression delta G is minus T delta S. So therefore, you have a maximum decrease, okay, at that particular point. Okay. So if you have a two component system, then maximum change in Gibbs energy will happen if you do a exactly same proportion if you put the two gases, 0.5 mole fraction if you keep them. Okay, so I hope this part is clear to you.
Excuse me, sir. I had one doubt in the diagram that you shown on next page. Sir, here, so for spontaneous process, we said delta G should be less than 0. Sir, but if we see the overall reaction from, if it is going from 0 to 1, sir, then the delta G is equal to 0. Sir, but if we talk about mu, then it is less than 0 for initial, and then after some time it is greater than 0. Sir, so for spontaneous process, should we say that mu should be less than 0 instead of delta G?
No, actually, see what it means is that mu is less than your mixture chemical potential is less than that in the pure form. See, basically you are talking about same thing, whether you are talking about G, delta G or delta mu. Whenever we write in terms of mu means we are talking in terms of one of the components. Mu is component wise, okay. Ith component, jth component, like that. And when you are writing in terms of delta G means it's the overall changes. Overall change in the Gibbs energy due to the due to mixing of all the components. So if you take one of the components in your mixture and then you deal with chemical potential, then also you will get the exactly same. So now in that case, your change in chemical potential in the mixture will become simply mu minus mu star. Understood? For the ith component.
Yes, sir.
Okay, and that delta mu, okay, delta mu for ith component, again you will see that will become 0, less than 0. Okay, because you will not have the summation term that will be just only basis of one component. It is like you are mixing it. Now, suppose there are 10 gases I mix. So each one of the gas will have some contribution in decreasing the Gibbs energy.
Yes.
So if you do that summation, suppose everybody does minus 2, minus 2, minus 2. If you have a 10 different components, is minus 20. So this is basically nothing but sum over contributions of all the components. So Ni mu I, you see that. Okay. Clear?
Yes, sir.
So if you take mu and find out the difference, you will get the exactly same negative change in chemical potential with respect to one particular component. And yes, here we are talking about that same thing. Now we collect for data from all the components and find out what is the overall change in Gibbs energy. That's what the sum of summation sign comes. So
Yes.
whatever property G shows, remember that mu also will show the same property. Okay, in terms of spontaneity and all.
Yes, sir.
When you take one particular component, you talk about chemical potential. When you take about the overall, including all the components, then you talk about the corresponding Gibbs energy. Okay. So therefore, you can very easily show when you will have a maximum decrease in chemical potential or Gibbs energy and maximum increase in entropy of the system. Okay. So this was important for us for discussion on the open system. Okay. Now quickly let us we'll talk about. We'll not go into details, but just to bring in the real systems. Okay. See, we discussing most of the time in thermodynamics. You will see people talk with the ideal gas or ideal solutions and all, because it is easy to frame relationships when there is particles are ideal. That means there is no interaction between them. But it is also necessary, and sometimes it is important also, so that you switch from idealized system to real systems. Okay. Now, when you switch from ideal system to real system means what? You are basically involving the interparticle interaction between the different systems. It is then expected, or it is desirable actually, that you preserve the same form of expression that we derived, the same form of expression that we got for the ideal systems or ideal processes. The same form we retain. Okay, then it will be easy to understand, and also the deviation from the idealist behavior can then be started in a very simple way. Okay, so what I'm trying to say is that when you go from ideal system to real system, what one tries to that is that keep the form of the expression similar. Okay, and then you try to find out what is the deviation from the idealist behavior to the real behavior of the system. Okay, so you try to preserve the same form of expression, similar type. That is what all the everybody tried to do that. So let us see how. Now for ideal gas, we know that for ideal gas chemical potential for one component, again, because when you are talking about one particular component, we write in terms of chemical potential. Okay. We can write it down like that. Okay. Assuming that P by P0, that P0 is 1, we can neglect that P0 because it doesn't come in the actual picture. Okay. Now for real gas, Lewis introduced this term, it is called fugacity. You have heard about it. It is called effective pressure. Now in the ideal gas, what is the difference between effective pressure and real pressure, or in ideal pressure? Now in ideal gas, since the particles are not interacting, so they are basically freely moving within the system. Only thing is that they only collide with the particles out on the wall. Okay. So therefore, the pressure is some value, whatever it has impact rate of collision on the wall, that gives you the pressure. But now in the real system, the particles are actually interacting with each other also within the container. So two types of interaction can happen. One is that there is a attraction between the particles, we talked about a little bit earlier, and there can be repulsions. Normally attraction interactions are more prevalent under normal conditions, and repulsion becomes very important at a very kind of an extreme conditions, like a very high pressure, when you force particles to come very close to each other, because repulsion is always much shorter range interaction than the attraction. So then only repulsion becomes important. But nevertheless, two possibilities, either attraction or repulsion. Okay. So now what happens, a particle's movement is not as free as it was in ideal situation. Okay. See, other particle present in the system will try to drag the particle back, or will try to push it further. If the attraction is more dominant, what will happen? The particles will pull it back inside the container. Or if the repulsion is dominant, then particle will push that particular trapped particle with a further it will increase its momentum or velocity. So it will impact with a greater effect on the wall. So that means this, we talk about now the effective pressure. Okay, effective pressure is the actual pressure that is experienced. Okay, considering the realness of the particular system that you are dealing with. Okay. Now this pressure, this effective pressure can be greater than the actual ideal pressure or can be less, depending on how the interaction happens. So in general, since I told you that idea is to retain the simplicity of the equations or the form of the equation expression similar way. So he writes mu equal to mu 0 plus RT log. Simply instead of pressure, he is now writing, he is using another symbol and he calls effective pressure fugacity Fi. Now, what is this fugacity then? Then he defines that for ideal gas, of course, then F equal to P, because there is no interaction between the particle. So it is exactly same as the, if you put ideal gas, F becomes P, you get this expression. But for real gas, F and P, they are not identical. If they are identical, it's an ideal gas situation. So if their ratio is equal gamma is not equal to 1 for real gas. Okay, or you can write it down like this: F is simply a gamma into Pi. So this gamma term, this is actually a measure of non-ideality. How much your system is real, how much it is deviated from ideal situation. That this gamma takes care of it. Gamma controls. So this is known as the fugacity coefficient or activity coefficient. Normally in solution we talk about activity. In gas we talk with the fugacity. So this is the basically a very important quantity which is a measure of the non-ideality. You also write it down like that mathematically. Basically for ideal gas means what? Ideal gas means if you take the ratio at a very low pressure, if you take, then normally gases will be well dispersed among themselves. So there will be practically zero interactions. So under that limiting condition, you can assume the ratio to be 1 at a very low pressure. So at a very low pressure, real gas behave like ideally. Because very low pressure, so that means they are well separated from each other, so much separated that that distance is so large that you can effectively consider them, they are not interacting at all. So therefore, they become, real gas will behave ideally at a very low pressure. Very low pressure. Otherwise, under normal conditions, when you say low pressure means basically the regular normal pressure. What happens? Generally, attraction will be dominating because the particles are highly, particles are basically happy in the container under normal conditions. So that means they are possibly attracting. Attraction is felt by them. So therefore, attraction dominates. Now, if the attraction dominates, then what will happen? Then the effective pressure that will be felt, by the container will be less than the ideal pressure, because now attraction is dominating. So the particle is being pulled back. Okay, when it tries to approach the, towards the wall, someone tries to pull it back because of attraction. So the effectiveness will reduce now. So gamma will become less than 1 when attraction is important. If the repulsion dominates, which will happen at a very high pressure, then what happens? Particles will like to push back because they are already under repulsion is very strong. So they want to just be separated from each other. Okay. So in that case, effective pressure will increase because they are pushing each other, the particles. So compared to ideal situation, the effective pressure that will be felt by the particles will be higher now. So therefore, we are calling F is greater than P. Fi will be greater than P. In that case, gamma will become greater than 1. And gamma equal to 1 for ideal behavior. So therefore, this gamma coefficient, it's a measure. So looking at its value, whether it's greater than 1 or less than 1, you will be knowing whether which one is dominating, whether attraction is dominating or repulsion is dominating, and that will affect, and eventually that also says whether your effective pressure is less than the true pressure or ideal pressure, or it is more than the ideal pressure. Okay. Now, same thing can be, just translated to solution phase, because many times we'll talk about chemical equilibrium in the next class. So, we talk about this activity and all. So in solution phase, simply we maintain the same relationship. See, in thermodynamics, this is important. You would like to retain the form of the relations and then change the parameters or bring in some kind of coefficient, some kind of parameter which takes care of the deviation. Okay, that is the whole idea. So ideal solution, see, instead of now pressure, we write in composition. That means the mole fraction. Okay, we write it like that. There are different ways you can write composition. Mole fraction is one of the ways. Since we are used to with that, so you can write down mu equal to this, mu I0 plus RT log of xi. This is for ideal solution. Again, ideal solution means very, very dilute solutions. There is no almost interaction between the particles in the solution phase. If you take a non-ideal solutions, now again, non-ideal solutions, your mole fractions, your effective concentration, again, here we use the term effective concentration. Here we say effective pressure for gas. Here we are talking about effective concentration, which is known as the activity. Okay, effective concentration known as the activity. So this effective concentration may be different than the true concentration. Okay, so in non-ideal solution or real solution, we write in terms of therefore we call activity, and this activity again is connected to it by this parameter we call the activity coefficient. Okay, here is fugacity coefficient. Here we call it activity coefficient. So again, AI will be equal to xi if gamma equal to 1, that means for ideal solution. Otherwise, they will be different. Okay, again, this is the limiting value when real solution will behave ideally. When at a very infinite dilution, you already know, at infinite dilution or under extremely dilute condition, a real solution will behave ideally. So otherwise, again, depending on the gamma, you will know whether your effective concentration or activity is actually greater than the true concentration or whether it's less than the true concentration. Okay, so this thing also maintaining the similar expression, one studies this real solution in a similar manner. Okay, so I will stop here for today, but real system we will not go into further detail because we don't have that scope now to go into the further details. So we will just introduce these. I thought of defining these coefficients, fugacity activity coefficients, and what is the effective pressure and effective concentration or activity, so that we know that we will be using these in the whatever in the equilibrium that we talk about next class. And also for you in general, you know that what we talk about in the real gas or real solution systems, we essentially write in terms of activity or fugacity, effective pressure. So this is important conceptually. Okay. So I will let me first